Today we're going to be looking at how to solve linear systems using a method called the Gauss-Jordan method. Now before we get into the Gauss-Jordan method, we have to talk about matrices and what matrices are. So, a matrix is a rectangular array of numbers enclosed by brackets. Each number in the array is called an element or an entry. Now, depending on what you're trying to represent, your matrix could be different sizes. They could be as many rows or as many columns as you would like, but they are rectangular arrays of numbers. So for example, we have a system of three equations here. 2x plus y minus z equals 2, x plus 3y plus 2z equals 1, and x plus y plus z equals 2. Now we can represent this system of three equations using a matrix, and in fact we actually use what we call an augmented matrix. So this is what it would look like. Now where did all these numbers come from? These are all the coefficients on the left for x, y, and z. You'll notice that in the system of three equations here, everything was written such that we had the x term, then the y term, then the z term, and then the constant on the right of the equation. In the first equation, we had 2, 1, and negative 1 for our coefficients of x, y, and z, so we write 2, 1, and negative 1. In the second equation, we had 1, 3, and 2, so we write that in the second row, and in the last equation, we have 1, 1, and 1. On the right-hand side, this is why we call it an augmented matrix, because we're drawing this line coming after all these terms where the equal sign would normally be. And then to the right of that, we write the constants, which would be 2, 1, and 2. Now, when we're working with matrices, there are a couple of what we call row operations that we can do in order to transform a system. So some of these are interchanging any two rows, multiplying the elements of a row by any non-zero real number, or adding a non-zero multiple of the elements of one row to the corresponding elements of another row. So in the first one, interchanging any two rows simply means you can change the order of the equations. You could instead write the second equation first if you prefer. In the second one, multiplying the elements of a row by a non-zero real number, that simply means when you multiply an equation, the entire equation, by a number that's not zero, you can do the same thing when it's in matrix form. The last one, adding a non-zero multiple of the elements of one row to the corresponding elements of another row. Now this is actually what you normally do when you are solving by using elimination. You're multiplying one of the equations by some number, so a multiple of the elements of one row, and you add it to the corresponding elements of another row. Now, notice what you cannot do. You cannot, say, subtract the same number from every element in a row. The reason you can't do that is because these are not simply just numbers, but numbers that are coefficients in front of variables. So normally if you had x plus 2y equals 4, you wouldn't be able to simply subtract 1 from everything in that row, from everything in that equation. So you can't do that either in matrix form. So what does this have to do with the Gauss-Jordan method? So the Gauss-Jordan method is actually an extension of the echelon method. So here's how it goes. The variables and the constants are lined up in the equations, with the variables on the left and the constants on the right. Once you have that, then you can write it in augmented matrix form, just like I showed you earlier. Now once you have it in augmented matrix form, then you will use row operations in order to transform the matrix so that it has zeros above and below a diagonal of ones on the left of the vertical bar. So for example, say you had two equations and you were writing it in matrix form. After you have it in matrix form, in order to transform the matrix into the form that we want, you want it to look like this. So on the left here, you see how there are 1s going across the diagonal, and then 0s everywhere else. If you had 3 equations and 3 variables, this is what it would look like. So you have 1s again along the diagonal, and you have 0s everywhere else. Now, once you've completed all row operations so that you have this diagonal of 1s, this is actually what we call the identity matrix. Once you have that, then your solution is going to be what's on the right-hand side, what I have right now as just written as blanks. Whatever you wrote down as your first variable, when you lined them up, say you had x, then y, then z, then as you read down the column on the right, that's going to be your value of x, y, and z. Let's take a look at an example. Write the augmented matrix for the system below. 2x plus y plus z equals 3, 3x plus 2z equals 4y minus 7, and then x plus y plus z equals 2. Okay, first thing you want to do to get this into augmented matrix form, you're not solving it here, is you want to line up the variables so that they're the same in each equation. And then on the right-hand side, you'll want to have the constant. In this case, we'll keep the first equation the same. The second equation, I'm going to subtract the 4y over to the left, and we can keep the last equation the same. Once you have that, now we can write this in augmented matrix form. So we are going to just write down the coefficients, so that would be 2, 1, and 1, and then a 3 on the right, and then 3, -4, and 2, with a -7 on the right, and then in the last equation, 1, 1, 1, and then a 2 on the right. If for any of the equations you don't have one of the variables there, so for example, let's say in the last equation, instead of x plus y plus z equals 2, you just had x plus z equals 2, then you can write a 0 where the y should be. Let's do an example where we actually use this augmented matrix form in order to solve the system. We'll start off easier with just 2 equations and 2 variables. So we have x plus 5y equals 7, -2x minus 7y equals -5. Now the equations are already lined up, so we can go ahead and put this into augmented matrix form. So that would be 1, 5, -2, -7, with 7 and -5 on the right. Now remember, our goal is to get a diagonal that has 1s with 0s everywhere else. Remember that we can only use row operations as we defined earlier. So we can switch the rows, we can multiply an entire row by a non-zero value, and we can add any multiple of one row to any multiple of another row. So take a look here. What we're starting with, we actually already have a 1 in the first spot. So that's good. The next thing I'm going to do is I'm going to try to get a 0 right below it. Right now it's a -2. So one way I can go about getting a 0 there is I can multiply the first row by 2, by +2, and then adding it to row 2. So if I multiply the first row by 2, I would have 2, 10, and 14. I'm going to add 2, 10, and 14 to -2, -7, -5. That gives me 0, +3, and +9. So now I have the 1 and the 0 where I want them to be. Next, I'm going to look right next to the 0, and I see there's a 3 there. I want that to be a 1. Again, you cannot simply subtract a number from an entire row, because these numbers are representing the coefficients of terms. So what I'm going to do here, you can multiply, or divide in this case, divide row 2 by 3. Or you can say that as multiplying that row by a third. So that leaves me with 0, 1, and then 3 on the right. Now I still have a 5 that's left where there should be a 0. So what I can do, again, I need to think about how I would be able to change this. Now there's no way for me to divide in order to get 0. So I'm going to have to multiply the second row by some number and then add it to the first row in order to get it to equal 0. Now, looking at what we have right now, if I multiply that second row by any number, that first term is still going to be 0. So when I add it to the first row, it won't affect the first term. So that first term will stay 1 the way we want it to. So in this case, let's multiply the bottom row by -5 and add it to the first row. So in the bottom row, if I multiply by -5, I would have 0, -5, and -15. I'm going to go ahead and add that to row 1, and that gives me 1, 0, and -8. Now notice I don't actually change the second row. I'm just using a multiple of that row to add to the first row. So now in our form, we actually have what we said is called the identity matrix on the left, and on the right, now I have -8 and 3, and we know that in this form, whatever you end up with on that right column, the rightmost column, is going to be our solution. So that means x is equal to -8 and y is equal to 3. Let's do one more example. X plus 2y equals 5, and then 2x plus y equals -2. Now let's start by writing this in our augmented matrix form. So we have 1, 2, and then 5, and then 2, 1, and -2. Now, let's see what we can do in order to get this left-hand side to be the identity matrix. So we have the 1 in place already. So I'm going to go below that. I know that should be a 0 there. So in order to get 0, again, it doesn't look like we can simply multiply or divide by anything. In that second row, we're going to have to add a multiple of the first row to the second row. In order to get 0 there, it looks like if I multiply the first row by -2 and add it to the second row, I'll end up with the 0 where I want it to be. So if we multiply that top row by -2, again, I'm just using the top row to get that multiple. I'm not going to actually replace the first row. That gives me -2, -4, and -10. Adding that to the second row, that gives me 0, -3, and -12. Now I have the 0 where I want it to be. Now next to the 0 I have -3, which I know should be a 1. So in order to get this to be 1, I can divide that second row by -3. That is going to be 0, 1, and 4. Now we almost have this completely in the form that we want it to. The only thing is that 2 that we have in the first row. That needs to be a 0. Again, we can't subtract a number from one row. And we can't divide in order to get from 2 to 0. So we'll have to do some combination of multiplying one row and adding it to another. So in this case, if I multiply the second row by -2 and I add it to the first row, then I'll be able to make that entry a 0 instead. And when I multiply that second row by -2, that first term in the second row will stay 0, so it won't affect the very first entry, which is a 1. So I'm going to add -2 times row 2 to row 1, and again, I'm not changing row 2, I'm just using a multiple of that row and adding it to the first row. So if I were to multiply row 2 by -2, I would have 0, -2, -8, and I'm going to add that to row 1. That leaves me with 1, 0, and then -3. Now that we have our identity matrix on the left, on the right, we have our solutions to x and y. So x is equal to -3 and y is equal to 4.